equilibrium of a particle. We will start with example 2. In the following figure, the body has a mass of 76 slugs. Find the tension in cables A, B, C, and D. So just when you have English units, okay, the force you will have will be in LB. How we should think in such problem? So here we have several cables connected together, and the purpose is to hold the block, okay? In general, when you have such problem, try to start from the point where you know more information. So here, you know the mass of the block, so you know its weight, okay? So if I say, since I know the weight here, then I can know the tension in this cable, okay? Because if I take the free body diagram of the block is in equilibrium because it's held by the cable. So if this is the weight, and this is, let's call, if you want, the tensions in the different cables, let's say this is T1, this is T2, this is T3, and T4, T5, okay? So we have here, we need to find these 5 unknowns. We need to find tension in all cables. So of course, we will not do it in just one step, okay? Now, to start with, the easiest one to find is T1, since T1 is connected to the block, okay? So if I take the free body diagram of the block, I can say that I have here T1, and I have here the weight of the block, which is equal to M times G, okay? Now, in English units, pay attention, G is not 9.81, G is 32.2, okay? So when you have mass in slug, you multiply by 32.2, you get the weight in LB, which is the English unit of force. Now, so from equilibrium of the block, so for the block, I can write that sum of forces along Y equals to 0, and always specify your directions. So I will take Y, let's say like this, okay, and this is X. So Y and X. And since my forces here are along Y, I will apply the equilibrium relation along Y. And also you can put close to your equations the positive direction, so to remember. So here you have plus T1 minus W equal to 0. So it's plus T1 minus mg equals to 0. So T1 is equal to mg. So now, since I know the tension in cable 1, I can move to the analysis of this point here. This point is joining 3 cables, but I know the tension in 1 cable because you know the tension is the same over the cable, okay? So if I found that T1 is equal to mg, then if I do any cut at any point of the cable, I will have T1, okay? And if I consider the cable, this is the cable, okay? If I want to draw the free body diagram of the cable, the block will push it down, while this point here will push it upward, because a cable can only sustain tension, okay? So by action-reaction, how the cable will act on the point? It will act down, okay? Because this is the presentation here is the action. So this one, this force here, okay, represents the action of the cable on the action of the point on the cable, okay, of the point on cable. And since I am interested, yes?
In this case, aren't all cables affecting T1?
No, no. The only thing affecting T1 is the weight. T1 is affecting the tension in the other cables, okay? But the other cables is not affecting T1. T1 will only be dependent on the weight, okay? And based on this, the other cables will act. And you find T1, and the value of T1 will affect the others.
All right, thank you.
Okay? Because you
So
know
we
this
just
from
take
the analysis. If you take the block as the free body diagram of the block, for equilibrium, T1 should be equal to the weight. So if you vary the weight of the block, T1 will vary. Okay?
All right, so we take basically the tension that is connected to the body at specific points.
Can you please repeat the question? I didn't hear you well.
So we take basically the tensions that are connected to the body at specific points. So in this case, because we're studying the weight in this case, we take T1 because it is directly connected.
Yes, it's
the
directly connected exactly to the block. Yes.
All right.
Okay.
Thank you.
Since once you isolate your block, if you do this, when you take the free body diagram of the block, you are isolating it like this. So the only cable in contact with it at this location is this cable.
Yeah.
Okay, this is why you put on the block weight and T1 on. Okay. Now, when you consider this point here, this point is attached to the three cables. So you will have the action of cable 1 on the point, cable 2, and cable 3. Okay? So here, this force here is the force of cable 1 on point 1. Okay? Which is equal and opposite to the force of the point on the cable. And we have seen together that if I take the free body diagram of the cable, what do I have? I have from here, I have the weight, but we have demonstrated that the weight is equal to T1. Okay, W here equal to T1. Okay, and we have from this side, since it's a cable in tension and in equilibrium, it's a massless cable. Okay, so no weight for the cable then. The tension is uniform across any point of the cable. So this is the force of point 1 on cable 1. And by action-reaction, the force of the cable on the point will be equal in magnitude, opposite in direction. This is why here you have, if you represent the force of cable 1 on the point, it will be downward. Okay? And always, because any cable is in tension, the action of the cable on any body will be directed towards the cable. Okay, so if we do similar analysis, cable 2 will act on the point like this. Okay, because the point will act on the cable outward. So by action-reaction, I take the opposite. And cable 3 will act on the point towards the cable upward. So now I have the presentation of the three forces acting on the point, and I am ready to apply the equilibrium relations. Okay? So once I draw the free body diagram of the point, it becomes very simple. All I have to do is to project on two directions, x and y. So starting by here, it will be easier to start with which direction you think? Y or X?
Y.
Very good. Why? Because
we only have one unknown.
Exactly. Along X, we have two unknowns, C and D. However, by projecting along Y, D does not have a projection. So when we project along Y, we only have the weight and the projection of C. Okay? And the projection of C is equal to what? I know, look, the angle here is given. The angle between this cable and the horizontal is equal to 60 degrees. So the projection on Y is simply equal to T2 cosine or sine 60. You can do or sine 60 or cosine 30. Okay? So the first equation, by projection along y-axis, I have plus c sine 60 minus the weight, since the weight is downward, equals to 0. So this equilibrium relation will give me my first unknown, which is the tension in this cable. Then as I called it C, we called it T2, so it's fine. You can call it whatever you want. Now, Once we have the value of C, now we can move to project on x-axis. So if we do projection on x, we have first the projection of C force, which is C cosine 60, and minus D equals to 0. We replace C by its value here, we get the value of D. Okay, so in this way we have solved for our two unknowns. Any question on this?
Doctor, I have a question.
Yes.
Anna, I honestly forgot how we get C sine 60 or C cosine 60.
Okay, no
Could
problem.
you quickly repeat how?
Yes, sure, I will. Okay. When you project a force into xy components, okay, this means that you are doing the perpendicular projection. Okay, so this is, let's say, your x-axis, and to project on x, you do a perpendicular projection like this. So this is a 90 degrees angle. Okay, so you can say that this triangle here is a right triangle. Okay, and this length here represents cx, and this one represents cy. Okay, now in this triangle, if you know one angle, okay, you can find the projections, because you have that where is your hypotenuse? Your hypotenuse is this one, which is C. Okay, this is the hypotenuse in my triangle. So the cosine of an angle is the length of the adjacent edge over the length of the hypotenuse. Okay, so you can say that cosine 60 is equal to Cx over C. This is why Cx is equal to C times cosine 60. Okay, so always look, if you have an angle, what is the side that is adjacent to the angle? This side. This side is adjacent to this angle. So I do C cosine 60. While the opposing side, okay, for the opposing side, you do sine 60. So you say that sine 60 is Cy over C. Okay, so Cy is equal to C sine 60. Okay, is that clear?
Yes, thank you, doctor.
Okay. Okay. Another, okay, we did not finish here. We are done with the first three cables. We still have cables A and B, okay? So we need to find tensions in cable A and cable B. Now, since we want to find A and B, which point we should take into consideration now? This one, because this point is connecting the cables A and B. So now I move to draw the free body diagram of this point, okay? And I apply the equation of equilibrium. So since I know the angles, so I can draw on my free body diagram the forces with their corresponding directions. So the tension in B will act on the point upward towards the cable B. Also the same for the tension in A, it will act towards cable A, so it's up. And for the cable C, it will act on the point downward, because as we said, the cable is always in tension. So by action reaction, you can find the effect of the cable on the point. Now, the value of C is already calculated in the previous step. This is why it was easier to start from this point, okay? Because when we started from this point, we had only two unknowns, C and D. If you choose to select C as a first point, then you will have three unknowns, A, B, and C. So you cannot solve directly. You need to go back to this point, then to solve again here. Okay? This is why, in general, try to start from the point where you know more forces, which is this one, since you know the value of T1. So now, since C is known, I have only two unknowns, A and B. Okay? So all I have to do is to project on X and Y, I will get a system of two equations with two unknowns. So let us start by projecting along X. So here, this is the angle of 30. So as we said, the adjacent side is Bx and the opposing one is By. So when I project on X, it's B cosine this angle. So it's B cosine 30. Now for A, as you can see here, the projection of A is negative. Okay, so I put a minus. And since the adjacent angle is 40, so it's minus A cosine 40. And finally, for C, also the projection is negative on X. This is why I put a minus. And the angle is with x-axis is 60. So I put minus C cosine 60 equals to 0. This is my first equation. My first equation includes two unknowns, so I cannot solve now. I need to go to the second equation. For the second equation, I project along Y. Along Y, I have first the projection of B. So since along X it was B cosine 30, so of course along Y it will be B sine 30. And it's positive because it's an upward projection. For A also it's in a positive projection, so it's plus A sine 40. And finally C has a negative component along Y, so minus C sine of the opposing angle, which is 60. So now I got two equations, equation 1, equation 2, with two unknowns, A and B. So I have a system. Please be familiar with how to solve with the calculator, to not doing it by hand. Okay, it's very simple. If you don't know how to do it, just tell me. In the calculator, you have an option to input a system and you will get the two unknowns. Okay, just you should put them in order. So if your first coefficient is for A, in the second equation also it will be arranged that the first term is for A. So you put in the calculators, this is my first term, this is my second, and C is equal to this number. And you do the same for the second equation. The first coefficient is this one, the second is the coefficient of B, and the third coefficient is the one after the equal. Okay, and you get your two unknowns A and B. And in this way, we have solved for tensions in all cases. Any question on this problem before we move to another one? Okay. So now another problem. The springs AB and BC have a stiffness of 500 Newton per meter and a non-stretched length of 6 meters. Determine the horizontal force applied to the cord, which is attached to the small pulley B, so that the displacement of the pulley from the wall is 1.5 meters. So what do we have here? First, we have two springs, okay, that are initially in this position. They are between A and C, and B is just at the middle. Here, look, pay attention. Here they said that the unstretched length is 6. This corresponds to the total unstretched length, okay? If they didn't mention this directly, but if you look at the figure, it's clear. Because at the initial position, point B was here, and the total distance separating the two springs, so from the first point to the end point, is 6 meters. So for each spring, the unstretched length will be 3. Okay, so L0 for each one is 3 meters. Okay, now we are applying a force on point B in order to move the springs a certain distance, which is 1.5. Okay, so this distance is 1.5, and the purpose is to calculate the value of the force F required to do this job. Okay, so in order to find F, since F is applied to B, so it's of interest to draw the free body diagram of point B. So if I draw the free body diagram of point B, I have the force F and I have the tension in each spring. Okay, this is T1, this is T2. Now, since if you look at your figure from symmetry, it's clear that the angle here is equal to this one. Okay, so due to symmetry, I have theta here and theta here. Okay, now who will tell me, can I say directly that the tension in the two springs is equal?
Yes.
Why?
Because the stiffness is the same.
The stiffness is the same, and I
Because
have
we have
a geometrical symmetry in my problem. Okay, I have
Doctor,
yes.
sorry, but when we have a pulley, aren't the two tensions equal?
No, look, it's here. It's a little bit different. It's not the concept of a pulley with a cable around it. Okay, so here, if you want, it's a different pulley. So we just this pulley, all the cable and the springs are attached at its center. Okay, when we say that the tension in the cable is the same, it should be going over the pulley. It should be like this. So this is a cable. It's going around the pulley and continuing down. Okay, here it's different. Here you have the cable and the two springs are connected to the center of the pulley. Okay.
Yes, thank you, Doctor.
Okay, so here you can say due to the symmetry in the figure and the symmetry in properties, same stiffness and symmetry in unstretched lengths and in the figure, then the tension is equal. And if you didn't pay attention for this, you can find it by calculation. Because if you do sum of y here, what will you get? You do sum of y equal to 0. Since I have the same angle, okay, so let us call this is T1 and this is T2. If I didn't pay attention that they are equal due to symmetry, if I write the sum of y equals 0, I will get the following. I will get plus T1 sine or cosine along y. If I want to project, yes,
Sine.
exactly, it's sine, yes. So if I want to project along y, for T1 it's plus T1 sine theta, and for T2 it's minus T2 sine theta. So if I write it here, T1 sine theta minus T2 sine theta, since theta is common between the two due to the symmetry in geometry, so if I take it into factor, okay, I get that T1 is equal to T2 equal to T. Okay, so this is the equation. So the symmetry is equivalent to sum of y equals 0. Okay, now in order to find the value of t, I need to project on x, and I need to know what is the value of the angle theta. Okay, how to find the angle theta? I should go back to my figure. Theta is the angle here between these two lines. Okay, I already know the distance here is 1.5, and at the initial position, since the cables are unstretched, I know that for each one the length is 3 meters. So I can say that tangent of theta is 3 over 1.5. Okay, so I can find easily theta by saying that tangent of theta is equal to 3 over 1.5. And then to find t, all I have to do is to project on x-axis. So I have sum of x equals to 0. Now, as you can see here, since the two tensions are equal and having same angle, so I can just write 2t times cosine theta, okay, and minus f equals to 0. So I get the value of, I get a relation between t and f, because f is also unknown. So I am not done, or because in this equation I have two unknowns, t and f. So to find f, I should find the value of t. How can I find the value of t? T is the force in what?
T equals Ks.
Exactly, because I have a spring. Okay, T is the force developed by a spring, And I know that in a spring, the developed force is K times delta L. So all I have to find is what is the value of the stretching of my spring. Since I know the initial length, which is on the unstretched length L0 equal to 3 meters, and I can calculate the final length of each spring by using Pythagoras theorem. Since here in this right triangle, I can say that AB is radical of 3 square plus 1.5 square. Okay, so from Pythagoras theorem, I can find L final, and I know the value of L0, the unstretched length. So delta L is simply L final minus L0. And once I find delta L, all I have to do is to multiply by the stiffness. The stiffness is given, so I can get the value of the tension in Newton. And once I find T, I replace back here in this equation, and I can calculate then the value of F. Okay? Any question on this problem?
Doctor, how did we get 3 point يعني L final, please?
Yes. L final, if you look in this, L final is here. Is which length? It's AB. Okay? You need to find AB. How to find AB? You know that this distance, this perpendicular distance, okay, is equal to 1.5 because they told you that we are moving the point in the horizontal direction a distance of 1.5 meters, okay? And at the initial position of the spring is unstretched when the whole distance here is 6. And since you have two springs, this means that each spring has an unstretched length L0 equal to what? Equal to C, okay? So initially, this is the unstretched length L0. And when you push point B 1.5 meter, the spring is stretched. And the length of AB, you can get it from this right triangle by doing the Pythagoras theorem, which is radical of 3 square plus 1.5 square.
Yes, thank you so much.
Okay, another problem. Here we have a system of pulleys. A block is supported by a system of pulleys as shown in the figure. Knowing that the system is in equilibrium and assuming the pulleys are frictionless and massless, determine the weight of the block. So here we have a series of pulleys holding a block, okay, and we are applying a force of 50 lb here at the end of this cable, and we want to determine what will be the corresponding weight of the block. Okay, please pay attention. Some of you might say due to equilibrium the tension here should be equal to the weight. It's wrong. Why? Because we have here several pulleys connected to the block, and we will see together that what is the main objective of putting several pulleys is to hold very high mass object with a small force. Okay, the system is widely used to elevate bodies with very high mass by just applying a small force. And you will see how this is possible in this problem. Okay, so to start with, I will do the analysis from here. For example, they started by drawing free body diagram of A until D. I will do for you the reverse procedure, and you will see that you will get the same result. Okay, why I choose to use the reverse procedure? Because I don't know the weight of the block, but I know the force here. The force here is 50. Okay, so since this force is known, I can start to do the analysis from pulley D. Okay, you know, we have seen that when we deal with frictionless and massless pulleys, the tension will be the same over the pulley. Okay. Guys, please, just 1 minute, okay? I will get back to you. Sorry guys, I'm back. Okay, so here we start by pulley D. Okay, so for pulley D, we have the force of 50 lb here in this cable, and this force is the same over the cable. So if I want to find the force in this cable here, it will be equal to 50. Okay, so this is 50 lb. Okay, and this cable is rolling over pulley C also. So I will continue with the same tension here, since the same cable is here. I have the same cable. So anywhere I do a cut in this cable, I will have the same tension, which is 50. Okay. Now, once I did this, now I can consider the free body diagram of pulley C. If I consider the free body diagram of pulley C, I should isolate C. If I want to isolate C, I should cut like this. Okay? So I am cutting at 3 places. Here, I am cutting the first cable in 2 points. The first time here, the second time here. Okay? And it's the same tension for the 2 points. So I will have 50 here and 50 here. If I draw pulley C, I will have a force of 50 upward because the cable is in tension here, and also a force of 50 upward here. So in total, I will have 100 Newton upward, or 100 lb here upward. Okay.
But
So
doctor,
now, yes,
how did we know that
I still have,
the rest of the strings are 52?
yes, because look, it's the same cable here. Look, follow the cables. Okay. Here we started by this cable from this point. This cable is going up, it's going over the first pulley. Okay, it doesn't end yet. It's continuing down. I am moving with it. It's turning over C. The end of this cable is here at the ceiling. Okay, so from the figure, if you follow the cable, it is just one cable from this point to this one. Okay. So this is why when I do a cut here, I should have the same tension because the tension is not changing over the cable. And when I do a cut here, since I'm still in the same cable, I also have the same tension. Okay?
Okay, thank you.
Well, now, if I go back to the free body diagram of pulley C, okay, I have a 50 lb force up here and a 50 lb force up here. And now I can find from equilibrium what will be the force here. Okay? Because due to equilibrium of my pulley, since it's massless, I don't put a weight. I don't have a weight for the pulley. Okay? So I have here 50 and here 50. So what will be the tension in this cable, which is attached to the center of the pulley down? It will be 100. Yes, exactly. It will be 100 to maintain equilibrium. So now, this cable, this is a second cable. I will draw it for you. The second cable will start from here. It will start from the center of C. It will go over B, and then it will go up until this point. So at any location in this cable, I will have the same force, which will be what? Which will be 100, okay? Because I have calculated that the force at this level is 100 lb. So now, since I know what is the value of the force in this cable, I can isolate now pulley B. So if I take now pulley B as my system, when I isolate B, I will cut in 3 places. I will cut here, and I will cut cable 2, which has a tension of 100 lb, and I will cut this cable also at another location. So now if I draw the free body diagram of B, so this is pulley B now. For pulley B, I will have 2 upward forces, and each one will have a value of 100. Okay. Then I will be able to calculate the tension in the cable that it's attached to the center of B. So if this is 100 and this is 100, So of course the one downward will be 200. Okay, so now I deduce that in this cable, in the third cable, the tension will be 200. And this cable is going down, turning over pulley A, and then it's attached to the ceiling up. Okay, so here, what will be the tension in this cable? It is equal to 200. Okay, now in a similar way, I know the tension in this cable. Now I can isolate pulley A. And when I do this, if I draw the free body diagram for pulley A, so this is pulley A, I have the upward forces will be each equal to 200 lb, and therefore the downward force will be 400. Okay, so this is 200 and 200. Okay, and the downward force will be equal to 400. Okay, then the force in this cable here, in the final cable, is 400. And since this cable is attached to the block, if I draw the free body diagram of the block, I can deduce that the weight of the block should be equal to the tension in this cable. So the weight will be equal to 400 lb. Okay. And we got their same result. Okay, now I will tell you what was their procedure. Instead of starting from pulley D back to A, they started from A. So if you choose to start from A, you don't know what is the weight of the block. You will express all forces function of the weight. Okay, so if you start from A, since this cable is attached to the weight, okay, then the tension in this cable is equal to the weight. So the force pulling the pulley A downward is equal to the weight. Okay, and when we isolate pulley A, in order to have equilibrium, then each force here should be equal to W over 2. So this is W over 2, this is W over 2. Then we can say now that the force in this cable here is equal to W over 2. So when I isolate pulley B, the force acting on it downward will be W over 2. So each force here in the upper side will be equal to W over 4. And since here I have W over 4, when I isolate C, then the two upward forces will be each W over 8. And finally, since I got that at this level, the force is W over 8, this force is equal to 50. So I end up with W over 8 equal to 50. Then I deduce that W is equal to 400 lb. And I get the same result we did together. Any question on this problem? Okay, so I will open a new session to continue the chapter, okay?